So in our department, we have been addressing collective adaptive systems in many different respects. I just pick one of them, which is socio-technical systems and complex human behavior. So if we think of how individuals behave mobility-wise, say in public places, then we do encounter phenomena that are best explained in complexity science. So if we take this collective of individuals, but this could also be objects in the Internet of Things. This could be software agents on the Internet, but could also be individuals in the street. Then we do know that these are forming a dynamic network. It changes over time. The topology of the network changes over time. And all of these individuals, they act in parallel. So what they do is they constantly have in observation their environment, their surrounding, what other objects, entities are doing, and they adapt their individual behavior according to what they see. So acting is constant, and it is a constant reaction to the behavior or to the observation of others. So control in this case tends to be highly dispersed. It is totally decentralized, if you want. There is no global central control. It happens all locally. And if there is any coherent behavior in such collective, it has to come from competition and cooperation. So people work together or they are competing against each other. And the effect is just this compound of these micro reactions. And here is the problem. The problem is that all these micro interactions, which are based on the rationale of the individual behavior, piles up to the collective. Then we observe a macro behavior, which is a phenomenon on the, if you want, on the global scale. And the problem is that these micro interactions cannot be combined in a simple mathematical formula, so that that formula would give the global behavior. This is not possible. This is the principle of a complex system, of an emergent system. So while these local interactions all happen all the time, all in reaction to the observation of other individuals, there is no way of explaining from the pure micro interactions what the global behavior, the macro behavior would be. This is the challenge. And this is a grand challenge of collective adaptive systems. We see that in very, very many fields of application. One specific instance of this collective adaptive systems problem that we have addressed is crowds in public places. How humans move in places in their free time. There is part of an explanation for crowd behavior that we can learn from biosystems like swarms. Think of a swarm of fish. Think of a swarm of birds, of ants, of bees, etc. There is a mathematical, simple model to explain the swarm behavior. And it goes back to micro interactions, which are guided by very, very simple rules. Rule number one is separation. The individual tries to keep distance to other nearby individuals. We also call this a short-range repulsion. The second rule is alignment. So the individual tries to go in a herding approach with the mainstream of the rest of the individuals. And the third rule or guiding principle is cohesion. This means that individuals tend to go towards the direction where the global neighborhood is going, we also call this the long-range attraction. Long-range attraction. So the individual tries to go together with the group. So on one hand, there is short-range repulsion. On the other hand, there is long-range attraction. And this explains how swarms of fish go together. But now, it is not a trivial extrapolation from swarms of animals to swarms of human beings. And what comes into play when we are looking at crowds of people is their rationale of making decisions. So they have a reason why they make certain movements. They have emotional states. They have whatever can be called signals of attractions that they are following. And this is not represented in these three simple rules that go with the animal flocking behavior explanation, the separation, the alignment, and the cohesion. There is something more complex. Nevertheless, if we look at how groups of people behave, and we did do this in the context of the Vienna City Marathon. The Vienna City Marathon is a mass sports event. It's the biggest sports event in Europe. It attracts some 50,000 active athletes, and it is being observed by more than 400,000 spectators along the road, and many more on TV. What we did in order to understand the movement patterns of spectators along the running track through this historic city of Vienna, Austria, was that we provided a smartphone app. And with that smartphone app, we asked people to share data that is collected from sensors embedded into those smartphones, so that based on that sensor data, we could calculate how the individual behavior, movement behavior of one of these spectators influences the masses and vice versa. So we must think of the smartphone here as a multi-sensor platform. What does it have? It has a geopositioning sensing unit. It has an acceleration, a magnetometer, a gyroscope sensing unit. It has noise level sensor units embedded. It has light density, if you think of the cameras, sensing units on that platform, and it is wirelessly connected. So if we take all together this sensor information, and if we put that in place with all the other sensor data streams from other such platforms, we can reason about patterns, okay? So in this case, we rolled out this smartphone app, and we had more than 27,000 users willing to share their data just for this event and just for that day, and just for being in place in the city of Vienna. And we calculate the density of spectators and map it back onto the street map of that city. And the first parameter that we are interested in is density. What is density? Density is the concentration of individuals per square unit space. And we plot this with a kernel density estimator, as you see it here, and color code that density. So low levels of density would be colored yellow. The more it goes into the red, the higher the social density. Density with this concentration of individuals per unit space is, of course, an indicator for a potential hazard that might happen here, maybe group behavior that turns to danger for the individuals that are involved here. Okay? So density is this first parameter that we are looking at, and this is plotted here in a dynamic animation for the Vienna City Marathon that was given in 2015. What can we say about this density in numbers? First, think about people standing. How many people per unit square meter would you assume to feel still comfortable if they are compacted on that small space? It is about seven persons per square meter, which is the threshold from where on people tend to feel discomfortable. If it gets more, you feel more and more uncomfortable. If it's less, you feel more and more free and relaxed. So about these 7 people per square unit of space as a threshold for a standing crowd, but has on the other side way lower thresholds as soon as this crowd gets moving. If people walk, so if they have their own directed move, then we know everything is fine if there is about half a person per square meter. If it gets to 2 people per square meter, then involuntary interactions happen because body parts touch other body parts, which is not a certain danger, but which is maybe observed as something that is uncomfortable. If we raise the number of people per square meter as a walking crowd, then we see that at the level of 3.5 to 4 people, this gets more and more uncomfortable as a situation. And if we climb up to 5 walking persons per square meter, we are already approaching a potentially dangerous situation. So in this case, danger is already advised to be alerted, yeah? As opposed to the 7 with the standing. So, and here we were interested in this way how the individual behaves with respect to the movement of other individuals, and how this influences the global behavior, namely the mass behavior of these people watching the event. And there we came to the conclusion that density as such is possibly not the ultimate indicator for a hazard. We would also have to look at the speed at which people are moving, at the velocity towards a certain direction, and that would be a better indication than just the density. In addition to speed, but it would be even more expressive if we would also calculate or look at the directions at which this speed is being expressed, and we end up into a mathematical expression that we call turbulence. Turbulence is the irregular flows characterized by a random displacement into all possible directions of that moving crowd. Okay? And there is, on top of turbulence, yet another mathematical expression to indicate the potential hazard that the moving mass is running into, and this is called crowd pressure. This goes back to Helbing and Johansson, and it is a quantification of this hazard that comes from the local pedestrian density, but also the variance in their local velocity. So if you take these 2 terms, you multiply the density, the local density, times the variance in the local velocity, you end up with a parameter that is indicative for a hazard that this crowd is running into. So these are the achievements that we have found. At least we can visualize those mathematical parameters of crowd hazard as a measure of this potential danger that the crowd is in. And from that we can learn. And now comes into play where and why we think that we have implemented a collective adaptive system. We do give that view back to all the users of the app so that everyone can see what is the actual hazard that is in the masses, so that the individual, based on that global information, can make local decisions to go there or to not go there. And the potential effect that we have from this is that if people see hazard areas, based on their rationale, they would not join in there. And with that, we have a collective adaptive systems in that we collect information from the individual behavior, from the micro behavior, and we combine and consolidate that individual behaviors into a picture. We show that picture back to the individual, which is expressing the global behavior, and with that picture, the individual makes a new individual micro interaction, decision. And this is the mechanism to prevent from crowd disasters. Yeah, coming back from this very specific complex adaptive systems problem to the more general fundamentals of collective adaptive systems concerns, we must see that we do have a world population of 7.3 billion people on planet today, which is highly equipped with information and communication technology systems like personal computers, like watches, like smartphones, like technology integrated into cars, into furniture, into clothing, into literally everything. And the numbers are high. If you just take smartphones, we have 6.3 billion smartphones in operation today. We have 1.3 billion cars on planet, most of them driving with navigation systems which are internet connected, electronically steering people from one place to the other. We do see smart watches on people's wrists. We do see smart glasses worn in each and every day work and life situation. All of these connected to the internet, all of these equipped with sensors, collecting data, giving rays for an analysis of these micro interactions, which again would give a globe spanning picture about the state of the planet, if you want. And with that global information being fed back to inform, at least, not to maybe recommend individual action on the micro level, we do see many, many shades and many, many instances of this collective adaptive systems idea. It was a very strategically important decision by Europe to raise this question and to bring it to a research priority in the fundamentals of collective adaptive systems research program. So over the past 3-4 years, European researchers have started to look not at just the cases of swarm intelligence and human behavior in masses and how technology like smartphones is inducing behavior in certain situations, but also in analyzing stock markets and the sensitivity towards the trading behavior of individuals or the trading of computer programs like bots into the congestion avoidance behavior for semi-autonomic vehicles driving on our roads, etc., and many, many other of these instances of such problems. have looked at these from a very fundamental point of view, knowing that there are so many instances that demand the right design principles for collective adaptive systems. And Europe is in a good way to have a foundational basis for these category of problems of collective adaptive systems. Still, research has to be continued here, but this is unique worldwide, also if we compare to other continents. So with this, I guess Europe has done a very convincing and a very dedicated, prioritized step towards research into a direction that is of ultimate importance for everyone here, as information and communication technology will pervade into our lives at all different levels, in all different instances. And we have to be aware, and we have to have the right principles of design and principles of operation of these technologies to get the best out of it for Europe and for the whole planet overall.